Welcome to the Cosmic Pie Podcast, episode 24, season 4. I'm your host, Wayne Barkhouse.
And I'm Robert Moore.
We are broadcasting live from the campus of the University of North Dakota here in Grand Forks, where Robert and I are presently melting.
Yes. I saw a wonderful meme yesterday from a friend of mine. Had last winter's temperatures on the map, minus 20, minus 25, things like that. And below it was, like yesterday's map, 102, 103. And it was, if you can't handle me at my worst, you don't deserve me at my other worst.
All I was thinking was 100 degrees Fahrenheit. My car registered that on my way home from work yesterday. Right. And I'm just glad, like we in North Dakota, it wasn't minus 100 degrees Fahrenheit.
Which you never know.
We haven't gone that extreme, but we certainly have been in like around minus 40 some, if I remember right.
Right.
And that's when you go outside and you feel like crying. It's so cold. Now
if you did that, you'd have icicles hanging down your cheeks.
Now you go outside and you feel like crying, but it's just too hot. We can't. There's no happy medium in there. Okay, Robert, so you want to start off doing disclaimers so that you get fired and not me, because it's all your fault.
Me?
Hey,
I just work. Oh, wait. All right, folks. Anything that Wayne and I say are the opinions of myself and Wayne. They are not the opinions of the University of North Dakota, College of Arts and Sciences, or the Department of Physics and Astrophysics. You have to come at us, folks.
Very nice. And, of course, if you like our podcast, we'll catch you early. Don't forget to give us a thumbs up. So put it in the right camera here. There we go. You see that? It's up. And also, of course, subscribe if you haven't subscribed. Now, let's start off talking about an asteroid. What do you think of that, Robert?
I like asteroids.
Torifune. Asteroid Torifune was imaged recently by the Hayabusa spacecraft, which was a Japanese spacecraft that, if you recall, did some measurements and scooped up some sample of Regu, if you remember that. And then it flew
from Regu.
Yeah, and then it flew by the Earth. Close enough, it dropped the payload into the atmosphere of the Earth, and the spacecraft continued on its way. And now it flew by recently within 800 meters of this asteroid.
Nice.
Now, this is one of these Apollo-type asteroids. It gets fairly close to the orbital sort of characteristics of the Earth in terms of our average distance from the Sun, which by definition is 1 astronomical unit. This asteroid is on a more elliptical shaped orbit, so its furthest distance from the Sun, as you see the numbers there on the slide, is about 1.26 AU, and at its closest approach, the perihelion point of the Sun is on the order of about 0.8 AU. So it definitely crosses the Earth's orbit, which makes it, number one, people might panic and say, oh, does that mean that at some point it may collide with the Earth? But there are other parts, of course, of the orbit you have to worry about. What's the inclination of the orbit? So how far out of plane is the asteroid? Also, where is the asteroid when it crosses the Earth's orbit relative to the Earth?
Right.
So if they're on either side of the orbit, then you never have to worry about them crossing or running into each other, that kind of thing. And, of course, the other thing I think about, and it works more for planets than it does with asteroids, because asteroids tend to move in their orbits, that if there's a planet, for example, that would not move appreciably since the beginning of the solar system, and the fact that it's still here after 4.5 billion years means that it'll never collide with the Earth, because it would have done that already.
Yeah, okay. Yeah.
But asteroids, like I said, they do move around, right? There's a different Yarkovsky effect, and
with the planets, they interact with the sun,
and they give off infrared light, and that acts as a bit of a thruster. Even though it's really minute, it adds up after a while. So they can change their orbits, which is a plug for when we do a perfect, complete survey down to some size limit. of the average composition of these asteroids. You think of how much light comes from the albedo effect. We're not done. You got to continue to look and make observations because of the altering of the orbits.
Right.
So,
but
it's
to me, when I see something like this, or people ask me about it, where you've got orbital parameters that clearly seem to cross Earth, I always like to point out Neptune and Pluto, because when Pluto crosses Neptune's orbit, it's actually above Neptune, because of that inclination, and then the other plane's rotation of the orbital plane, so that when they actually cross each other's orbits, one's below the other, one's above, and vice versa on the other side where the crossing happens. So
yeah,
the same thing is probably going on here.
And John mentions a very important point. I thought that if you have asteroids that you should use preparation H, problem solved. It's actually preparation R for rocket. And the fact that one of the main reasons to have a space program, if you ever, come across somebody who says, why are we wasting all this money on this space program? Let's put it into something else. Let's feed the poor and, dress the all this kind of stuff, right?
And they're not wrong.
And they're not wrong on that. But we also need other things, as a complete, hopefully, society. And those other things is a space program. Because if we ever got in a situation where an asteroid, because of its altering of its orbit gradually over time, makes it a high probability collision with the Earth, we would have wished that we have developed a space program.
Right.
And so that's preparation R for rockets.
Yeah. Meteor and asteroid impacts are quite honestly the only natural disaster that we actually could stop from happening. We have the technology now. We just need to put the resources into building it. But, oh well.
I thought you were going to say AOL there for a second.
No.
That's long gone, Robert. Get with the times.
Give me my CompuServe.
Where's the bulletin boards that we can post messages on?
Right. Where's Mars and Citadel? Come on.
Well, speaking about spacecraft, a nice little update recently on what happened to the New Horizons spacecraft. And if you may recall, this is the one that flew by Pluto, first time that's ever happened, back in 2015 in July. And it got some magnificent close-up views of Pluto and its moons, including Charon, the largest moon that orbits around Pluto. Really great data. I mean, before that time, Pluto was just like a speck from the largest telescopes that we have. So obviously, getting a close flyby really improves what you can see. But New Horizons is way beyond, the orbit of Pluto now. In fact, it is approximately 5.9 billion miles, or about 9.5 billion kilometers from the Earth. And one of the things that it did after flyby of Pluto is that the scientists using telescopes were looking for another sort of target of opportunity, something that they could reach given the constraints of the trajectory that the spacecraft was on, and also the thrusters that's on board, and how much you can change your path, your trajectory. And they flew by an asteroid, you may recall, and that asteroid was similar to the one we just showed in that it was a contact type of asteroid. Looked like two asteroids that are glued together, right? You can envision the collision of the two bodies that form the bigger body. Now, since that time...
Probably more like rub.
Yeah, sticking together. A slow motion collision, everything slow-mo type of thing. Now, since that time, and I think that flyby of that asteroid by the New Horizons spacecraft was about 2 years or so after it flew by Pluto. And, of course, scientists were scanning around looking for a second target, after another asteroid, second asteroid, and they didn't really find anything that was in the right location.
Right.
And they are hoping that they would find something, and nothing has been found. So it's like, what do you do now? Well, there was calls, by people who have the power to give out money to actually cancel the program at that point. In other words, don't have anyone employed to watch the spacecraft, just let it go on its own and be done with. But others suggested that, instead of going by another asteroid, how about if we just monitor or sample what's going on with the environment out in the outer part of the solar system? So get information about particles, cosmic ray impacts, magnetic fields, all these kind of things. Kind of what the Voyager spacecrafts were monitoring, Voyager 1 and 2 for a long time. So in order to preserve, the power of the spacecraft itself, and it's one of these things where it's powered by the radioactive decay of plutonium, that you can shut down all of the instruments. Why do you need a camera if you can't? There's nothing really to take an image of. So shut down the non-essential type of instruments, and they essentially put the spacecraft in what they called hibernation. Now, it wasn't a true hibernation where you could think of nothing running at all except maybe the heaters to keep the computer operating and all these kind of things. What they did have running, though, was the collection of the data, as I mentioned, tasting, if you like, the environment, information about particles, about magnetic fields, and these kind of things. And when you're out that far, it's a real complex interaction of essentially what you get from the sun in terms of its influence, and also what you're getting from the general stellar field of the rest of the galaxy, where those kind of two influences interacts. You have this sort of interface, but the interface is not sharp at all. It's very diffuse, it's very fluid, and it changes a lot. That is, it has a lot of fluctuations in the location of this boundary of this transition region. So there are a lot of complicated magnetohydrodynamic sort of interactions and EM type stuff that's occurring in the outer parts of our solar system, and that's why it's very important to get some data on that. And each time the spacecraft kind of flies through one path or trajectory, you're getting one line of sight sort of measurement. But of course, ultimately, you like to have many of those, and we only have a very limited number of spacecraft that's doing this. Anyways, the New Horizons spacecraft woke up recently, a few days back, and now is in the process of transmitting its data back to Earth that it collected over essentially the last 11 months when it was sleeping. It's like, an animal, a dog or a cat sleeping with one eye partially open. That's kind of the thing that was going on here, which is kind of cool when you think about it.
I've never understood how that actually conserves power, since the power comes from the radioactive decay of plutonium, which happens no matter what. So, how are you conserving it by turning everything off?
Well, number one, you're not using all the instruments. And maybe if you can find an asteroid to fly by and alter your trajectory, then you can use the camera. So the hope is to preserve that. Plus, you're cutting back to minimum people power, right? So you don't need a team of people watching it.
Right.
So it becomes a very simple thing to monitor. And I think that's the heart of it.
Okay, because, what I was getting at is that the plutonium is going to decay anyway.
Yeah.
So that energy is there whether you're spending it or not.
That's true.
And it's not stored.
Right. And the other thing I would imagine is you don't use any of the thrusters either, right? Because you'd have to use the thrusters if you're sending back radio signals to the Earth, right? You have to point it in the right direction, and then you're using up the propellant on board. So that's some of the stuff you don't have to bother if you're in, hibernation mode.
Right.
Yeah, and so we also got exploring the what? How would you say that, Robert? I'll let you pronounce that.
Exploring the what?
You see it? The comments. Kawithra? What is that?
Exploring with the Ka with Ra. Yeah.
Okay. Anyways, he points out that it's plasma physics, and he said it's this field, heliophysics, and that's exactly right. It's very complicated interaction of E&M type of stuff, and the fourth state of matter, the plasma.
The stuff I got to admit I didn't like is a planetary and stellar formation guy.
Well, it's not easy, so it takes a lot of stuff.
It's not.
Exploring the Koth with Ra. Okay, great, thank you. Okay, so the next thing to mention is something that is going to show up later on and 2 days from now. Oh, sorry, before I get there, and it's related to this, by the way. There was also a report that came out from China, and of course, when they send out reports, they release them knowingly. It's not like you have independent press that's doing things, of course.
No independent verification?
Well, And what it was all about was their new version of what they call the Long March 10B rocket. So the Long March 10 has been used for many years now. So this is the 10B version. And the upgrades that they have done with the rocket is they actually bring back the first stage for reusability purposes, just like SpaceX with the Falcon rockets. And you can see an image of the first stage doing a soft landing on a barge out in the ocean. And in some sense, they're starting to catch up to SpaceX with this sort of, development of this technology. And the first stage, and there's physical reasons for this, uses both liquid methane as the fuel and liquid oxygen as the oxygen source, the oxidizer. And liquid methane is used because it has a very high specific impulse. So you can get a lot of energy out of it. And the other thing is, it's a lot easier to manipulate than using liquid hydrogen, which is sort of the best alternative. But that's a cryogenic fuel. In other words, you have to take hydrogen gas and compress it to a liquid. And that requires very cold temperatures. And then, of course, you need all the infrastructure around that. And that becomes very complicated.
And then it leaches into everything, turning it brittle from the cold as well. And the next thing you know, your rocket's exploding.
Well, just think of all the leaks, right? The SLS, the Artemis project, right? There's been leaks on every time. There's twice now they launched that rocket type, and both times they've had leaks. And because you're dealing with such cold, material, liquid in this case. So it's, China's catching up dramatically, and people will argue how they do this, and I won't go into that because I don't want to be let go from this job, even though we had a disclaimer. But of course, they're also doing lots of other stuff, and the physics. A lot of why do rockets look all the same essentially? Because it's the physics.
Because of the physics, right?
Right. You're not launching something that looks like a frisbee with its surface area, the greatest, going straight up against the air, right? If you're going to launch a frisbee, it's going to be sideways, slicing through the air because you minimize the cross-sectional area. I mean, there's physics involved in all this stuff. So
I agree. And
yeah,
it's again, people are like, why don't we just build our rockets in space? Because you still have to get all the materials up into space in the first place.
Well, just use a giant trampoline.
Right.
You remember when the whole stuff happened between Ukraine and Russia? Then Russia was talking, the head of Roscosmos was talking about not launching American astronauts into space. And this was way back, when there wasn't a SpaceX, a regular rocket to get, Dragon capsule to get to the International Space Station. And they said, if Americans want to go to the International Space Station, they just use a trampoline.
Right.
A catapult might be better, but
who knows?
But you got to have some way of getting stuff, like as you mentioned, into space in order to assemble it, if that's ultimately your goal. So,
I mean, I do have always questioned for cargo launch, at least, why we haven't used, something like railgun, launch system or something like that. But there's bound to be reasons why you can't. So I'm willing to sit back and say, okay.
And the acceleration on those type of devices is extremely high, like probably 20, 30 Gs or more, right?
Right. So like I said, cargo launch.
Yeah.
You're not putting people up with that.
No, don't send up a frog, but put up stacks of aluminum plating or something, or titanium or whatever, right?
Or water or what have you. Yeah.
Yeah. There must be some reason why people haven't developed. I know people have looked at it for many, many, many decades.
Yeah.
But it must, the energy to do that, getting through the Earth's atmosphere and all the heating effect and all of that must be a real stumbling block.
That's all I can think of.
Yeah.
There's something about the heating or putting enough energy into it to overcome the air resistance.
In other words, build one on the moon.
Oh, yeah. Definitely a railgun system is much better for the moon. But again, we got to get there.
Yeah. exactly right. Now, speaking about SpaceX, I just want to update people who are not sort of paying attention to this kind of stuff that we do have the next launch that, as last time I checked, is scheduled for Thursday, 2 days from now,
Okay.
at 5:45 p.m. Central Daylight Time. So this is the flight number 13, and they test fired the engines a few days back. So that's what you see on the slide here. You see the top, the Starship itself, and then the first stage being tested. And I don't know. I want success in all of this. I'm a big supporter of the space program, as you could probably figure that out. And it doesn't matter to me if it's government or private. I want people to succeed because I think ultimately that can benefit society if we use it in the right way. Right? Underline that,
Agreed.
please. And one of the things that SpaceX is supposed to do, at least they're contracted to do, along with Blue Origin, is develop a lander for the Artemis Moon project. And we're not going to get to the surface of the moon without a lander. I hate to say it. Unless you sign up for like a one-way trip or something, right?
Right.
But other than that, we need a lander. And so the SpaceX's version of a lander depends on Starship operating to where they want to use it for putting up a lander in Earth orbit and then sending it on its way to the moon. And also to land on the moon when they get there. And that's the whole sort of top stage part of this rocket assembly, is to do just that. So there are lots of testing that still need to be done. We'll see how this one goes. Wish them all success in the world, because that, no pun intended, because that's just going to speed up, getting back to the moon with people again.
Yeah.
So we'll see how this plays out.
That should be a goal. I mean, it should have been a goal a long time ago, but
too late now. Too late now. Can't cry over spilt milk, as they say, or non-activity.
I cry over it. You can't put it back in the carton.
Well, it's disappointing, right? Maybe that's all you can afford. Now you have no more money for any more milk. So there goes your milk till you get your next paycheck, and you have to wait 2 weeks or something. In this case, we had to wait almost a lifetime for potentially getting back to the moon. So how many people were, born between after the finishing of Apollo 17 and before the latest Artemis 2 mission? How many people were born and then passed away, unfortunately? So that's a whole, lifetime passed by, and we didn't do anything in that sense.
Yeah.
Not good.
No.
Now,
it really wasn't.
Speaking
it was
about
lost opportunity.
It was, unfortunately. I think we could have pushed it and developed it better and maybe been on to Mars by now and doing other exciting things. Who knows? But yeah, life gets in the way, as they say.
That's it.
Now, speaking about what's going on in space, we also give you an update of some things, very exciting things that's going on. One of them, as you see on the left, is an image of the Nancy Grace Roman Space Telescope. And that's due to be launched very, very soon. In fact, on August the 30th, so just over a month from now. And this, remember, is initially started by the giving of a telescope to NASA by the National Reconnaissance Office. It's a reflecting type of telescope, so it has a mirror roughly about 2.4 meters across. So it's very similar to the Hubble Space Telescope. In fact, it was designed probably, and I haven't looked at this in detail, but I wouldn't doubt it was designed initially to go on the space shuttle in the cargo bay as one of those military launches from the proposed Vandenberg, Air Force Base, space base, a independent launching site instead of going to Cape Kennedy, but it's all military, so it's all top secret. So I wouldn't doubt that's why they had that limitation a little bit on the size of the mirror. But they didn't need the telescope anymore, so they gave it to NASA, and NASA managed to get the funding to outfit it so that they can use it for astronomy-related observations. And the benefit compared to this telescope with the HST is that the Hubble Space Telescope has a much narrower field of view. In fact, the Roman Space Telescope, as you see here on the left, has a field of view 100 times that of the Hubble Space Telescope. So in a single image, with the Roman, you're going to capture an area on the sky equivalent to 100 exposures that you would need with the Hubble Space Telescope. And so that begs right away that you can do great surveying type of work with it. So you can survey a large area of the sky a lot faster than what you could do with the Hubble Space Telescope. So that's going to be, a very fantastic type of thing once it gets up there. And of course, the benefit of having it in space, you don't have to worry about the Earth's atmosphere. So you're working at essentially the diffraction limit of the telescope. And so, in other words, very high resolution. And also, some of the instruments are sensitive to non-optical type wavelengths, like infrared, for example. And so you can capture that a lot more efficiently than having that light pass through Earth's atmosphere, and some of it is absorbed and scattered mainly by the water in our atmosphere. So you can do a much better observation than in space in that sense.
And now we're being asked just how large a field of view it's going to have. I think it's on the order of 2 full moons or something.
Yes.
About a degree.
Yeah. So the field of view of the Vera Rubin Space Telescope, which is a ground-based telescope, if I'm not mistaken, that's closer to the order of 10 square degrees on an image.
Oh, wow. Holy
cow. It's huge. Because the dark energy survey was about 3 square degrees, and I think it was much greater than that, if I remember right. And so it's on that order anyways. And it's a specially designed telescope for the ground. It's an 8.4 meter mirror, but then the way they design it, it's effectively a little about a 6.5 meter mirror, because they have one of the tertiary mirror built into the center of the primary mirror. So I wish I had an image to show you of the actual design, but if you go online and Google it, you'll see what it looks like. It's really kind of unique, and that was to keep the length of the telescope as short as possible and also provide that very large field of view. And the reason why you want a large field of view, because the design initially was to be able to survey the whole southern sky. So the whole sky at where the telescope is located in Chile, observe that whole sky every 3 nights. So it take 3 nights to cover the whole sky. Well, if you're taking 3 nights to cover the sky on average, you must have a large field of view per image that you capture with your camera. So you really need, highly specialized type of telescope and instrumentation to be able to pull that off.
Now, there's a question I haven't thought of. Do you know if it's a deformable mirror? In other words, can they do adaptive optics and change its focal properties?
Yes, 100%. 100%. Yeah, it's adaptive optics. In fact, a lot of the engineering testing that they've been doing the last several months, a lot of it is because of this, the adaptive optics. Okay. It's a really complicated system to get it all to work together. And I'm going to show you one leg up on that, by the way. The survey just started, as we talked about last time, just a little over a week ago, the real survey, right, the meat and potatoes part of it. But it's a really complicated type of instrument, and everything got to work correctly, of course. So there's lots of computers and technicians that are watching everything to make sure it's doing what it's supposed to do. But there's lots of benefits to it, but one good benefit is if you're covering the whole sky every 3 nights, and then you observe again and again and again, so you build up on a single sort of location on the sky, you build up the exposure over time. So you can see fainter and fainter and fainter as the weeks and months and years go by. And it's initially forecast to have the survey last about 10 years. But if everything's working well and they can get more money to support it, I'm sure it will go beyond the 10 years. But one of the interesting thing is if you're taking an image of the whole sky every 3 nights, you have lots of opportunity to watch stuff move.
Yep.
And this stuff, quote unquote, can be asteroids and comets and all maybe things that we don't even know exist that's up in space because they're so rare, right? We just really didn't recognize them. But if anything is moving, we're going to be able to see it.
I got to admit, I'm hoping to start seeing Oort cloud objects because, we've seen the main belt, we've seen near Earth, we've seen the Centaurs and the Apollos and all these others. Kuiper belt. It's time to see see the Oort cloud instead of just saying, well, it has to come. The orbital parameters of this comet say it has to come from there. Well, let's see it,
And of course, what captures people's imagination nowadays is the fact that we've detected 3 interstellar bodies, that is, objects that are not in bounded orbit around our sun. They come in from outside our solar system, wherever they originated. We don't know for sure, of course. So how many of those objects actually pass through our area of space that we'll be able to capture with this telescope just from the fact we can see stuff move? And of course, there's a lot of data being collected. So it requires somebody who worked as my second postdoc on the data management system of the Dark Energy Survey when I was at a postdoc in Illinois. It takes a lot of heavy duty processing by computers and sophisticated algorithms to be able to process all of this data. It's a huge petabytes of data over time that's being collected. And if you're looking for something that's moving, you take an image of area of the sky, you have software that runs to be able to detect all the objects and measure their brightness and different filters, and then you got to take an image later on of that same location and compare now your new catalog with the previous catalog to look for things that have changed position. And that way you're looking literally, the needle in the haystack type of thing. So looking for objects that move. And of course, there are objects out there that we know about, tens of thousands of asteroids. So there are satellites that are going to be in the way because we're on the ground looking through the atmosphere and then through space. So we're going to see any satellite that's out there. And I'll illustrate that a little bit later on too, what that means. So it's all kinds of the stuff that that we're going to detect, and it's the algorithm development, and a lot goes into that. Maybe we don't appreciate it as much. A lot of brain power that went into optimizing these codes so that we can get to the objects and the data that we need, in a timely fashion. Right. What happens if we find something, but nobody found it until 5 years after the observations were taken, and now this object is long gone? Maybe it's one of these objects that flew in the inner part of the solar system and then on its way back out. And then we can't do any new observations because nobody knew it existed at the time.
Right.
So that's the thing.
How many astronomical findings have been of that type? Hey, we got to looking at Hubble's plates, 80 years later, and look, there's this.
Yeah. And so other telescopes, both in space and on the ground, can do a lot of follow-up too. If you find some interesting objects, and you can investigate it in detail, not with this telescope per se, but use other telescopes to do targeted observations. So it'll guide us to where we should be pointing and capture the interesting science, the interesting phenomena that's out there in the deep, dark universe.
Don't patronize me, boy. I know what space is. Space is death.
I'm looking for von Neumann type probes that are
there we go.
Orbiting our sun. Can we find them?
That would be just a phenomenal discovery. I'm not gonna lie. I'd love to see something like that coming at us.
Well, if we find something,
not if it was a big swarm of them, but you know what I mean.
As long as it's not like the beginning of the Borg getting here.
Right.
Well, if we find anything interesting, we'll ask Extra Bull if we can go on his podcast and talk all about it. How's that?
There you go. I like that.
I'm sure he don't mind. Now, the image on the right is actually, I think, Robert, we talked about this project, very exciting one. This is of the Dragon spacecraft. This is the one that's going to land on the surface of Titan, and it be launched in 2028, as you see there, and arrival in 2034. So eat well, whole food, plant-based diet, so that you're still alive in 2034 with the arrival of this spacecraft then on the surface of Titan. And it's going to literally, in situ, that is right direct sampling of the surface of Titan and images and taste the atmosphere to see what it's actually made of in detail. And then it has the ability, because it has a thick atmosphere on Titan, that it's actually going to move to another location, like a helicopter or a drone nowadays, as we would say, and do the same kind of thing. That is, it's going to fly around on Titan.
Yeah.
and sample different things and go up different heights to test the atmosphere to see what it's made of and if it changes, as you go up above the surface of several meters or whatever, or different locations. What's over that hill? Well, you don't have to think about it. Just go there with the spacecraft. So it's going to be...
More importantly, I don't have to be there.
Talk
about your North Dakota cold winter.
Yeah, that'd be a little hard on the lungs too, I think, if we were...
Oh, yeah.
But if you look carefully at... So what was this test? So this test was a vibration test. So just making sure the spacecraft can survive launch and anything else that will happen to it in its planned mission. And notice you could see the propellers. And some people ask, well, are those like covers over the propellers? The answer is no. The engineers don't put on those delicate propellers until the very last minute. So these have the right balance in terms of weight that you'd expect the propellers to have so that they can do this test. So they're mock propellers in that sense, or stand-in, if you like. But the real thing won't be put on until, like I said, just before launch, because they want those things to not be damaged in any way possible, right?
Yeah.
Extremely
airfoils
important.
Are a careful thing. You can't really play around too well. Or hydrofoils, fluid foils of any sort. Because their function depends critically on their shape.
Yeah. And of course, the first sort of proving ground that we used for flying drones, if you like, or helicopters on other planets, was the one when we went to Mars. You remember that? Mars. And so
that did phenomenally well. So we've got a history of this paying off. So run with it.
So not only have we done that, but of course, Mars, we have several rovers that are roaming or have roamed the surface of Mars. Perseverance and Curiosity are the two ones that are still active today. And here's a neat discovery. Robert, this kind of goes up your alley here on geology part of the thing. So this is the first report in the science journal Science of the discovery of essentially in situ or native sulfur from Mars' surface itself. It was actually, formed on Mars. It wasn't brought up from deep underground in some type of magma eruption in the distant past through volcanism. It actually, as far as they can tell, it was formed locally where this area was being examined by the Curiosity rover. And you can see Go ahead.
Yeah, it would have been hydrothermal in nature. Because what native sulfur, native silver, what all that means is it's not incorporated into any mineral other than itself. So this is elemental sulfur. It is native. It's not hydrogen sulfide. It's not a sulfile. It's, pure sulfur, elemental sulfur. And that is usually deposited in hydrothermal type scenarios. So.
Yeah.
That's still a nifty find.
It is, and it's all in the same area where the rover landed initially in this Gale crater. Cool. So it's spent years and years now examining this, right? And that's one of the arguments that people have used. We can send up rovers, don't risk anyone's life, right? They can sit in the cold of Mars and do all these wonderful things. We'll make them nuclear powered so we don't have to worry about the solar panels being covered by dust and the power level to drain to a level where all of a sudden it can no longer function. But if we had a team of geologists in Gale Crater for as long as Curiosity rover has been on the surface of Mars, for many years now, I would bet that the science team there would have produced a lot more results than what we're getting from the rover.
Oh, yeah. I won't disagree. I do think we need to be doing more with rovers because, to me, rovers are definitely the vanguard, if you will, the skirmishers. They get out there and find out what's dangerous, what's not, how to do things. Then we bring in the boots on the ground. But so I think if we develop the technology, we're about to the point where we need boots on the ground on Mars. Because a human will look at a rock and go, wait a minute, I wonder, and just turn it over. It happened on the moon missions. Whereas a rover will go, well, that's an interesting rock. They'll the data people will catalog it and everything and move on. Where that human on the ground will sit there and go, let's check that.
Well, I mean, a good example of that, right, was I think it was during Apollo 17 when we had a geologist,
Yes.
right, on the moon, and then they noticed the presence of orange soil.
That was it.
And there's certain I can't remember what it's called. Maybe you remember a certain mineral that was concentrated in that region to give it an overall orange appearance to the human eye. But I don't remember what it was.
I don't remember exactly what it was, but it was a metamorphic, if I'm not mistaken. So it actually gave insight into the chemistry and conditions of the lunar near surface, subsurface. So they got some insights into the actual formation of the moon from it. So,
and the thing is that it wasn't, as far as I know, it's not all over the place. It was just in this one location that they spotted. Right. So if we would have had a lunar rover in that general area, it may not even have seen it. Like, it never took an image, and you wouldn't know back on Earth, hey, there was something orange over here on the side of the image. Let's get the rover to explore it. If you missed it, didn't get an image of it, that was it.
That was it. It was done.
So Jack Schmitt, who was the geologist by training, then who landed on the moon in the Taurus Littoral Valley with Gene Cernan at the time, he actually gave a talk. This would have been back in 2005, I believe, either 2005 or 2006, when, once again, I was at Urbana-Champaign, University of Illinois, and he came to campus and gave a talk. And I actually went to it was 2005, I remember now, and he gave a talk about everything that happened on the moon during his mission, and also what has happened since in analyzing the material from the moon. And it was very interesting. But, a lot of these people are getting older now, and we're soon going to lose that firsthand knowledge that we had before. So that's another reason it's important to get back to the moon in a timely fashion before we lose all of that. And there's like decades and decades where nobody knows anything because the people who did know are long gone, type of thing. So, but eyes on the boots on the ground. That's what you need
for institutional knowledge.
Yeah. As an aside, that's why it's painful when you hear of budget cutbacks and different agencies like NASA laying a large number of people off. You just hope that the people that remain know what the other person was doing.
And I've looked it up. It's that he found glass spherules. So it was a spray from erupting lava that cooled instantly in the vacuum of space. And it's vibrant orange because of the high amounts of titanium and iron oxide in the glass.
So titanium and iron oxide are responsible.
There you go.
Yeah, cool.
So,
well, I mean, you could, yeah.
I was just neat stuff.
And it just means, we knew that it had titanium in a lot of that and the material on the moon's surface. So that can be processed to build things, right? Mm-hmm. If you need to.
The aluminum, there's a whole lot of bauxite and aluminosilicates in lunar surface. There's a lot of iron because the basalt, it's costly to refine it out, but it's there.
Yeah.
You really want it.
And there's also, of course, you can think about maybe extracting water from the polar regions, especially the South Pole. Mm-hmm. There's doubt on that now, as we talked about in the past. People have gotten better images with unmanned spacecraft in orbit around the moon, and you don't really see, it's not like you're driving around here in the spring and you see all the ground everywhere is, it's warm again. And then occasionally in the shadow areas, on the side of hills that face north, if you see like a little bit of ice laying there, you know what I mean?
Right.
It's not like that at all.
No.
So we can't envision that kind of thing. If there's any ice, it's buried underneath the soil to protect it from the solar radiation. Yep. So it doesn't, sublimate or something, right?
But again, you can always make the basic extract the basic ingredients for water from surface materials or the solar wind.
Yeah.
I mean, most of the lunar surface is silicate, so SiO2. Strip off the oxygen from the silicon, you've got your O2. Just have a big scooping up the solar wind, which is mainly protons, discharge them back into neutral hydrogen, burn it with the oxygen you just extracted, boom, you've got water.
Yeah.
The stuff is there. We just, how bad do we want it?
Yeah, we need to do a good job of processing it, applied engineering, yes, and be able to figure that sort of thing out. So it's not just helium-3 on the moon. There's lots more potential there as well. Yes.
Yeah. And then just the scientific base of it, the fact that, until they put a lot of satellites into orbit around the moon, we wouldn't need space telescopes. We just build them there. There's plenty of the raw materials. There's silicate, glass, SiO2. There's a lot of reasons really to go to the moon. It's just deciding we want to.
And the moon's one of those places, obviously, that everybody has seen, as long as you have eyesight that can allow you to see it. And in fact, the moon's been around in humans' sort of consciousness since we formed, if you like, or evolved to the point where we could have the intellectual capacity to look up at the sky at night or even during the daytime and wonder what's all about. Yeah. And sort of along that sort of line of thinking is the next topic.
Okay.
And this is kind of interesting. So, way back, the time of Ptolemy, and Ptolemy lived in an era where, and it depends where you live today on the world, of course, where what was going on in the sky was extremely important. And I'm talking about modern day, what we would call astrology. So what was happening in the sky, what the alignments of things that they would see, whether it's eclipses or other things, or what constellations you would see at the time that you were born, all this kind of stuff. It was extremely important. And it's really just, it's kind of a natural thing, right? It's just a human beings wanting to understand what's out there and assuming that it has some kind of an influence with what happens here on the Earth. There's a direct connection, if you like, with inner space and outer space type of thing. And one of the things you could do, and it was done, and a lot of this stuff, of course, is lost to history. We don't know what people did from different countries around the world thousands of years ago. But of the surviving records, people made what we say star atlases. They would note the location of stars in the sky. And this was done, thousands of years ago. And when you look at the records that are available, in museums and stuff, you'd notice constellations. Because a star in the course of 2,000 years is not going to really change its location relative to another star enough that you would notice it with the eye. Now, there are some stars, of course, that are close enough to us that they have enough motion that they move relative to background stars, but that's very rare. Okay, you have to do very careful observations. But the other thing we notice, and the first variable star, the star that changes in brightness due to a number of effects, could intrinsically change in brightness, or it could be another star that passes in front of it of a different brightness and therefore would dim or enhance the brightness depending. The first variable star was noticed back in the 1500s.
That was Algol, wasn't it?
No, it was actually a different type of star, Mira. It was Mira. Was first noticed in the 1500s. So that's relatively recently. That's just in the last 500 years or so. And yet people have been studying the sky, for thousands of years prior to that. But what did they notice? And did they think it was something else? Or, or if they did try to make a record of it, that hasn't survived and we don't know about it. It's lost knowledge and so on. And why I'm going through all this at great length is because people have gone through these star atlases, and the brightness of the stars relative to each other is something that if you want to call them ancient astronomers, had noted. So not only did you try to note accurately as possible the location of stars, and that allows us to see the constellations, but they try to, as accurately as possible, depict the brightness of the stars. And a lot of time it's done by the size of the symbol that they use to illustrate a certain star. So if you look at a star and it's the brightest one in the constellation, that would be larger on your medium that you're using to write on, whatever it is, paper or papyrus or whatever it is, and it's something that's fainter, it would be smaller in size, physical size on your drawing.
And lo and behold, we still use that system.
Yeah, it's just a natural type of thing, obviously.
Absolutely. Yeah.
And what was noticed is of the brighter stars, right, there was a particular star in the constellation Eridanus. And that star we designate today as Theta Eridani. That seemed to be a lot fainter today than it was back in the time of Ptolemy, when several individuals around that time had made these star charts. And the significant and the brightness difference is an estimate, of course. We don't know absolutely what the value is, but it's on the order of roughly 2.7 magnitudes or so. Now, the magnitude system, for those who don't know, if it's a star, it's a ranking system. And we're talking about apparent magnitude in this case. That is, how bright do the stars appear to be in the sky? So the brightest star would have the smallest apparent magnitude. So the sun, for example, which is the brightest star in the sky, then has a very small, very negative value. It's like minus 25 point something, you know,
I'll say,
depending whatever filter.
26.
Yeah, somewhere in that order. And stars that are fainter than that would have a larger value until eventually you get into the positive numerical values. So the faintest star you can see with the eye in a dark location on the order of about 6, apparent magnitude 6. The difference from one magnitude to another, for example, if you compare a magnitude 2 star with a magnitude 3 star, so they differ by 1 magnitude, that's a logarithmic scale. It actually translates into a brightness difference of about 2.5 times. So a magnitude 2 star would be 2.5 times brighter than a magnitude 3 star. This is a difference of 2.7 magnitudes. So take 2.7, raise it to the power of like 2.5102 or something like that. I can't remember the exact number.
To work those problems.
Yeah, and you get a difference in brightness and times, how many fainter it is compared to, you know, it is today compared to what it was back nearly 1,800 years ago. So it was, in other words, what I'm getting at is the brightness difference is large, and too large to be explained by errors in the map making skills of the astronomers back then. And people puzzled over, why is that the case? In fact, could it be that the star we're talking about was indeed brighter back then, 1,800 years ago, than what it is today? So it was actually a physical change in the brightness of the star? Is that what we're talking about? And this latest study that just came out, so it's a preprint from July 1st of this year, is, as far as they can tell, it is an actual difference in brightness. The star today, Theta Eridani, is actually about 2.7 magnitudes fainter than it was back in the time of Ptolemy. Now,
we've got a question about the magnitude system.
Right.
That wasn't it originally that the brightest star was magnitude 0 and the faintest mag 6? I think so, but
no, very close. So it's magnitude 1 and magnitude 6.
Okay.
And today being the late 1800s, when we decided to officially use that magnitude scale from Hipparchus, who used it initially back in ancient Greek times, is we define a difference of 5 magnitudes, a delta M of 5, which is the difference between, let's say, 1 and 6 magnitude. We say that equals exactly 100 times difference in brightness. And so we put that on the modern scale, which means measuring brightnesses electronically, like with CCD cameras and so on. And we can accurately, very accurately, that is, measure the difference in brightness and then use the equation that relates the difference in brightness to the difference in magnitude and put things, calibrate things on the same scale. So a difference,
gets some tweaks from time to time, like it did when we went from photomultiplier tubes to CCDs, and now CMOS chips are beginning to become popular. So,
yeah, and a lot of that stuff is based on known calibrated observations that people have done, like Arlo Landau. He's not with us anymore, but he essentially spent his whole career, academic career, on top of a mountain observing stars, looking for what we call standard stars and observing them over and over and over again. Because if you find a star and you think it's of a certain brightness and a certain filter, wavelength passband, you don't want that star to intrinsically change in brightness. You want it to be, absolutely constant. So then you can compare another star with that standard star and estimate what is the magnitude difference or the brightness difference of the two. And of course, you don't want just one standard. You like to have hundreds and hundreds of these standard stars.
And there, folks, is why I never got into absolute photometry, because you spend half your night looking at calibrator stars.
Well, not only that, you spend half your life looking at these standard stars.
Calibrator stars.
And that's what Landau did. He wanted to make sure these stars were not variable in nature over long periods of time. And the other thing is, with the invention or the construction, if you like, of these very large telescopes, which we'll talk about here in a second, optical telescopes in particular, the standard stars that people were using for many years are no longer applicable. You can't use them. Why? Because with a large telescope, these stars are too bright. They saturate the detector. So you got to find yourself faint standard stars. Right. And so you have to repeat this monitoring campaign of looking night after night after night after night over decades of these now very faint stars, trying to find standards that you use to calibrate your magnitudes. So that's kind of the work that's ongoing now. But it's one of those things that you do and you don't get nothing for it. Like, you don't get any awards or accolades for it, but it's extremely important.
Somebody has to do it.
Someone has to. It's the grunge work of astronomical observations. We'll put it that way, of photometry. Now, this particular object, this Theta Eridani, it's actually a triple star system. So there are 3 stars. And what was discovered with very good observations done with large telescopes is that these stars, at least 2 of them, reside in a common envelope, as we say. That is, they're close enough, they share material on the outside of their effective surfaces. And that material, of course, is not going to be, homogeneous and isotropic. In other words, it's not going to be completely smooth. It's probably going to be clumpy. So there are times when, and if it's far enough away from the star, it takes a long time, for example, a large clump of material like a dust cloud to be in front of the star relative to our location for it to enter the field of view and then go out the other side, if you like. And that could literally take 1,800 years or thereabouts. And so what we think happened is just that. There was an enhancement of material that lied in front of the stars relative to our location and nowadays blocking out the light coming from the star system, more so than 1,800 years ago, when maybe that clump of material was not in the line of sight of the Earth, and therefore it looked brighter back then than it does today. And if that's true, all you have to do, if you have the time, is to wait around several hundred years and see if the brightness of this system increases. You see, as that density moves out of the line of sight again. So it can be complicated. So if you see stuff changing, this is kind of the moral of the story, right? And it ties in with the Vera Rubin telescope. If you look carefully and see if anything changes. It's like you're out in the forest, a deep forest, right? And you're looking around. Let's say you have your camera with you, because we're going to be nice on this podcast. We have a camera and we want to photograph deer. Now, how do you find deer? Well, they're going to hear you first before they probably see you in a deep, dense forest, and they'll run away from you, right? Danger. But if you're very quiet and you move along very slowly and you're always pausing to be very still, one of the ways you can see a deer would be from its flickering of its tail, from its motion. If it's absolutely at rest, it's very difficult to see it because it blends in with the background of the forest around you. And so it's the motion that allows you to see the deer in this case. And so it is the motion of things that really becomes important here. If things are moving, it's much easier to spot them. And that's the same thing that's happening here in this case, right? It is from the motion of things and its effect on what we can see, like the brightness of the object, that allows us to find it in the first place, that captures our intention. Now, moving on, Robert, as I mentioned, we were going to talk about observations from Chile. In fact, the next slide will say more about this. But what I wanted to share with you is this recent study that just came out, published in the monthly notices of the Royal Astronomical Society, of experimentation of coding from the ground, so ground-based laboratory type of measurements, where people are essentially making different recipes to devise coatings that could be applied to these low Earth orbit satellites that will reduce the amount of light that's reflected off of their outer skin, if you like, and then ultimately reflected down on Earth. Now, the image you see on the right is taken from Chile. It's a 1-hour exposure. And look at all the trails you see from satellites.
Right.
You know, it's amazing. They're all over the place.
I'm working with a grad student and trying to get data. And just Friday night, he took a sequence of data between about 10 and 10 p.m. and at 2 a.m. And many of his frames had 2 or more satellite trails through. So, yeah, satellites are a problem.
So one of the things that this study is addressing is, can we design a special? Yeah, well, no, you can design a special coating to try to minimize or greatly reduce the reflected light.
Yep.
So that's something that we're trying to do. So we'll see how this goes.
Yeah.
So just a notice for people who are watching.
Anybody else is noticing it? Yeah.
Yeah.
You're breaking
tremendous amount of lag. Yeah, I know there's a tremendous amount of lag. I don't know if that's between you and I and going out on the stream or not. So we'll see. We're almost done, so we'll continue here. So the final slide is an update of the construction of the extremely large telescope. And this is the one the European Southern Observatory is building. It's a 39-meter diameter telescope. And this image is cool because it gives you a sense of scale. You see 3 people in the middle, and look at the size of the sort of the structure in which the mirrors are going to be, assembled on top of. I mean, this thing is massive when you look at it in scale.
Yeah. Wow.
In fact, as you see, they're all together. Crazy. It's going to have nearly 800 mirror segments all put together like a jigsaw puzzle to be an effective mirror, of a diameter of the 39 meters. So it's going to be the largest optical telescope in the world when it's finally is finished, and that should occur in the next year to 2 years or so. It will be ready.
For our American listeners, that's about the size of a football field, if I'm not mistaken, isn't it?
Well, given the size of them, it must be close.
Yeah. Wow.
Yeah, it's huge.
It's like, 39 meters. That's big. And then you visualize it and you start making comparisons, and it's like, oh.
And the historical thing about this, the funny thing was, when the proposal was initially brought forward to the European, governments that are involved in the European Southern Observatory Consortium, scientists, engineers, they wanted to build the OWL telescope, OWL, the overwhelmingly large telescope. And it was going to be 150 meters in diameter.
Oh, Lord.
But the government said, that takes a lot of euros. Maybe you should make one a little smaller, but just make sure it's larger than any of the planned optical telescopes from the United States so we can always have the record. And And the U.S. is looking at building
Yeah.
a 30-meter diameter telescope. So this will obviously beat that at 39 meters. In fact, this one will probably be online seeing first light before the U.S. Led telescopes are on the sky.
Such creativity in naming. Yes.
It is.
That's astronomers for you. We don't think in terms of, quarks and, leptons and things like that. It's a shovel.
It is. Now, if you are interested in how stuff like this gets built, how could you possibly engineer something that's, 39 meters across? Well, one of the ways to get involved in things like that is go to places of higher learning, like the University of North Dakota. And so we have come join us. We have lots of programs both online and on campus. We're a very dynamic type of environment. We have a new STEM building that's going up all the time, actively building even in this heat. The poor guys are over there banging away on the steel girders. So it will be constructed at some... Yeah, I don't either. I mean, it's supposed to open, at least the first part, phase 1, a year from this fall. So it looks like hopefully everything is on schedule to do that. But it's a real interesting campus. We have a lot of stuff happening on campus, a lot of new buildings going up, and hopefully lots of students that like to partake in the programs that we have here at the University of North Dakota.
Yep.
Now, Robert, we're coming to the end of the podcast, unfortunately. We always leave you with a quote at the end. Today's quote is related to what we talked about. That is the number of satellites in low Earth orbit and the impact of astronomy. And so the quote is actually from a paper from Nature Astronomy from 2023, so 3 years old now. And here's the quote. So it's from Felci et al. 2023. Here's the quote. The loss of the natural aspect of a pristine night sky for all the world is an unprecedented global threat to nature and cultural heritage.
I will agree.
So I think we have to be very careful. We have to be very careful in what we actually do and look out for the unintended consequences of our actions.
Yes.
Now, if you like this podcast, don't forget to give us a thumbs up. Our next podcast will be a week from now. That's on July the 21st. And so thank you very much for watching, and we'll see you next time.
Bye, folks.